used a laser, or if you had a special like sensor that's then re-emitted another light beam the other way, this argument would still work, right? All the essentials of this argument come from geometry, not from physics. You see that? Yeah. Right? The only thing we assumed was this. This is a good one. This one we can assume. Okay, so that's the definition of velocity, right? But this is the only thing we use. That plus the Pythagorean theorem are the only things we really use here. Meaning, this derivation is not dependent on any particular physical process. That is, it applies to all physical processes, because our argument here still works for anything as long as you can use the Pythagorean theorem in the definition of velocity. Right? Okay? So, from that we can say that this is not just about things bouncing up and down, but it's about all physical processes. That is to say that the time changes, becomes larger in this case. The time changes from people in different reference frames. Okay? That includes biological processes. There's no reason they should be excluded. There's no reason to believe they're not physical in nature, which means, anyone here of a twin? Yeah? Wow. You're not twins, right? Okay. Yeah, okay, good. So, if Maddie, your twin is named?
Garrett. He doesn't go through.
That's fine. Garrett?
Garrett.
Garrett?
Yeah.
Garrett. All right, so Maddie and Garrett are twins. Okay, here's what I mean. Maddie and Garrett are right now the same age, right? Okay. Now, what this is saying is suppose Garrett goes into another reference frame. He gets on a ship, travels very fast, spaceship, and travels very fast. Okay? He is now in a different reference frame from Maddie. According to Einstein, that means that time will pass at a different rate relative to Maddie, which means he goes on this rocket ship adventure and comes back and meets Maddie, and he is a different age from her, right? In particular, it turns out he'd be younger. Okay, so that means he goes on a 20-year rocket ship, right? So Maddie is now, what, 36, 37, something like that. And then he comes back, and he's 20. Okay? And they are physically different ages, right? Like, you know, he will come back having only had 2 years elapsed for him, or sorry, 3 or 4 years elapsed for him, right? And he will come back having, you know, being like a college kid and, you know, acting like one, and Maddie by then will be like, you know, I don't know, by then he could be married with kids and, you know, in the middle of your career and all sorts of other things, right? Like, they will be physically different. For Maddie, 20 years will have elapsed. For him, only 3 or 4 years will have elapsed, right? And both of them will be sure of it and will be surprised to see the other one, especially because you'd be like, where have you been in the last 20 years? Right? So this is Einstein's claim. You can see that it's kind of a big claim. You can see why other people would have rejected this one without going further with it. But we are saved, sort of, by the structure of this factor gamma. So let's look at the factor gamma. If velocity equals 0, then what does gamma equal? Take a look mathematically. If velocity equals 0, what does gamma equal? 1. Good. If you get 1 minus 0, right? Square root of 1 minus 0 is still 1, right? And 1 over that is still 1. So gamma equals 1. Since gamma is a factor, what that says is if Garrett got in a rocket ship that didn't move, then they would still be the same age. And we're good with that. That was not surprising. Okay, good. Let's look at what happens when velocity equals what's the fastest car, right? Any of you guys into cars, or planes or something?
I haven't heard of anyone that goes faster than 400 miles.
Yeah.
I think the last speed record is higher than that, but it doesn't really matter at this point. Okay, 400 miles an hour. Okay, we're just going to approximate here. 400 miles an hour, right? Does anyone offhand know the speed of light in miles per hour? Okay,
3.0 meters per second.
It'd be like 100, no. 10 million miles per hour, about. Okay, roughly, good enough. Okay, so So you have, then V squared is 16,0000, right?
Which is a large number.
It's a large number, yeah. Okay. Now, C is equal to 10 million. There's a scientific notation, huh? 10 million is 10 to the 7th. Okay.
Isn't it?
670
million miles per hour.
270 million? I'll find factor.
Is that miles per second or miles per hour?
670 million miles per hour? Oh, yeah, of course. Yeah. I did, that was miles per minute, but I forgot factor 60. Okay, call it 10 to the 8. That's 100 million. That's close enough. We'll be fine for now. So C squared is going to be 10 to the what? 16, right? Good. What's B squared over C squared then?
Well,
this is of order 10 to the what? Okay, good. So B squared or C squared is approximately what?
10 to the negative 11.
10 to the negative 11. Okay?
Very small.
What? Now we're going to take 1 minus 10 to the negative 11. What can you tell me about that number? It's very close to 1, right? And then you take the square root of that. What happens when you take the square root of a number that's close to 1?
It's
Less than 1. What
It's
happens?
closer to 1.
It actually gets closer to 1, right? So this makes it even closer to 1, okay? Just below 1. And then what's 1 over that going to be? It is a number that's just below 1. The reciprocal of it will be
Almost 1.
just above 1, okay? So in this case, what we have is gamma is almost 1. Okay? If you want to get the actual factor, if for average like walk around speeds, it's usually on the order of picoseconds, so 10 to the negative 12 is the common number, though if you're going faster, you can get up to negative 11 or negative 10. Okay? You can actually get an app that for your phone that uses the accelerometer in the phone to figure out how fast you're moving, and thus figures out how much time dilation you experience over the course of its data taking, and it measures it in picoseconds, right? It's trillions of a second, because that's how much the effect we're looking at, right? So this is why you never notice it, because this factor is so absurdly small that you never notice it, right? Is that a question? Yeah.
So you have to be going a few thousand meters per second in order to get even.
No, you gotta go a lot faster than that.
A lot faster.
Yeah. You can work this out numerically. It's not hard, right? If you just put in a few numbers. But basically, rule of thumb, you don't enter what we call the relativistic regime, right? The part where this gamma starts to matter until you hit 1/10 the speed of light. Okay. Less than that, this number is basic gamma, sometimes just about 1. When you hit 1/10 the speed of light, then even then it's still pretty close to 1, but it starts to matter. And then from then, the numbers start becoming significant. Okay. For example, what happens if we have a velocity of 0.5 c? This is an actual problem I want you guys to work out. What's gamma? You can do a calculator. I just want a numerical one. Okay. If you're real good at math, you can do it in your head, but there's no shame to using paper. I recommend the paper. Less likely to make mistakes.
What do you use?
And there's nothing wrong with taking the steps slowly to make sure you got it. That's fine. You don't need to show off.
It's gonna be
0.5 c or 1/2 c, right?
0.56, so it'd be
It doesn't matter if it's c in the equation. Don't convert c to numbers. It's okay. Just hang on. You have an answer, right? Or you have a question? Oh, sorry. Oh, you have an answer. Yeah, please. Don't convert c to a number. C in the equation, so it'll cancel out.
That's 1%.
It's the sort of thing you need to get used to doing. It's an important skill, and maybe it's been a little while since you've done some of this algebra, so. As simplified as possible. In particular, no square decimals, please. Convert to fractions. Convert to fractions. And then reduce.
So you can cancel out that, so 0.25 over C.
Fractions are a lot easier to work with. It's probably been easier to start with 1/2 C.
I'm grabbing calculator. We'll give this.
Very good question.
Makes sense.
Okay.
Please leave it in fraction form. Do not change to a decimal, that's not worth your time, right? Fraction form is preferred. Sort of like math class, right?
Wait, you want this in fraction form?
Sorry? You should be able to reduce it to a single fraction.
Yeah.
Okay.
I just
All
have
right,
to
who
give
was the
you my-
answer? Just want to see where we are. Okay. Hold on a little bit, please. This one. This is not a race. It does not matter whether you get a quickly or simultaneous limit, but I mean, this is not, it's not about, physics is never about speed. It's about understanding.
It's about velocity.
Okay, got me.
Time is
And
relative.
sometimes chemistry is about speed too, that's different. Alright, anyway. Okay. People have answers? Okay, good. This is important because we do it a lot. Okay? I'm going to go through it real fast. Well, not real fast. I'm going to go through it. Square root of 1 minus, I'm going to call it 1/2 C squared over C squared. The 1/2 will be easier. I should have written that to begin with. Okay? Decimals suck for this sort of thing. They get nasty really quickly. Fractions are much easier. Okay? So that means first you simplify that square, of course, becomes 1/4 C squared over C squared. C squares cancel, right? So you get 1 over the square root of 1 minus 1/4. Some of you, when you see this, you're like, oh, I know how to subtract fractions, and other people are like, subtracting fractions. So let me just go through this one.
It's 1.
If you got 0 over -3, that's wrong. So remember when you were adding or subtracting fractions, you have to get a common denominator. So you have to convert 1 to have the same denominator as 1 over 4, which means you convert 1 to be 4 over 4. That's right. So 4 over 4 minus 1 over 4. Now that you have the same denominator, you can just subtract the numerator, keeping the denominator the same. So you get 3 over 4. Okay. And then you simplify that square root, and you get the square root of 3 over 2. But you have 1 over all that, right? It's okay, reciprocals are super easy, right? It just means you flip it upside down, so your answer is 2 over root 3. Do we need to rationalize? No, waste of time.
Wait. Oh.
I know, right? Well, my math teacher, I still have no idea why math teachers tell you to rationalize your fraction. I still don't know.
Because it's fun.
Because it's fun. Wow. Okay.
No, it's not. It's just incredibly easy.
Sure, that's good reason. All right, fine. I don't consider it fun. I consider it another opportunity to make mistakes.
Yeah.
So no way to try to rationalize. It actually makes it harder to understand when you rationalize denominators. Like this is clear what's going on. You change it to 2 root 3 over 3, it's not as clear where it came from, right? In quantum mechanics, especially, we're going to have a lot of denominators with square roots, and then I want them to stay there. It's much clearer when they stay there. Okay. So do not waste your time rationalizing your denominator. Do math teachers here rationalize denominators?
Yeah.
Okay. I have no idea. Ask them why, because I still don't know.
I'm told that because before modern calculators
Easier to look it up in the log tables, yes. So that doesn't actually answer my question, because calculators came out a long time ago. I think it's just practice for you guys. I think it's just practice. There are times when it's the fancier ones where you have to complete the square and stuff like that is actually useful stuff you actually have to do. So I think it might just be practice for you guys. Anyway, you got enough practice. Don't rationalize your denominators. This is never do that. Yeah.
So you're saying my math teacher lied to me about why it's so important?
Well, what did your math teacher say?
She said that you had to do it every single time and it would be like that for the rest of your life.
Well, life is full of disappointments.
For example, me.
So, okay, so we got that one. Now let's look at a few fun ones. What do you get if D equals C?
You get 1 over 0.
Wait, what?
Wait.
You're having it equal the speed of light.
Not so good, right? No. You have what's the word for it?
Undefined.
Undefined, good. Gamma is undefined.
Wait, so that's
Do you know what undefined means in physics?
Well,
Do you
that
have
and
my
a
answer?
bunch of other
wrong.
reasons.
Doesn't mean it's wrong. It means it never happens.
Yeah, not possible.
It's undefined, it doesn't happen. It's like great.
Oh, that isn't. And then
I hear what you're saying, John, and it doesn't make sense. It doesn't ask this equation. Just saying. What happens if E is greater than C?
you get a negative number, so it's also
Going back in time.
What do you get?
undefined.
Irrational
You get a
numbers.
what?
Imaginary.
Imaginary number, right? You get the square root of a negative number, which is, you get gamma is imaginary. Also negative.
Yay.
There's one over I equal negative I. So, what does that mean about going faster than light? I can say this. No, it doesn't mean, because it doesn't actually mean that. We will get there later. I mean, it's not possible. We will get there later. What it means is that our equations are not going to give sensible lines of something. Okay? V, remember, is the velocity of a what?
Speed.
No, not of an object.
Oh, the reference.
Reference frame. A reference frame is a coordinate system that moves. It is not physical. It is a mathematical construction. Okay? A reference frame, therefore, you can explore whatever you want, right? What this tells you is, if your reference frame goes at this speed or faster, you'll get answers that make no physical sense.
So try to keep
That's
them-
all it says. That doesn't mean you can't go faster than the speed of light. It says that your reference frames don't give reasonable answers if you try and do that. Okay? You can go faster than light, but we'll talk about why later. It's not that simple. Yes, sir.
The speed of the Earth is it fast enough to have any significant impact on your reference of time?
Is the speed of the Earth fast enough to be relevant to this?
Yes.
No. Nowhere close. I mean, relative to what, I should say, but you mean relative to the sun? No. Nowhere close. Nothing goes, nothing except subatomic particles and light go anywhere close to the speed of light. It's way too fast. If the flash actually moved at the speed of light, there would be a variety of problems that would arise. If you look at XKCD what if number 1, you can get some of the consequences of it are pretty awesome. It's pretty awesome. Okay, now, Jay, right? Yeah. Good. Jay asked a good question. How do we know which time is the one to use? This is very important. We need to look at it. So let's talk about that exact question. Here's how it works. When you measure a time, you have a stopwatch in your head at least, right? There's a stopwatch and you start and you stop, right? How do you know when to start and when to stop? You have to decide on 2 events, right? So you always have time is measured, right, between 2 events. You say, when this happens, I'm going to start. When this happens, I'm going to stop. Right? 2 things happen. There's 2 events, two occurrences that cause you to start sometime. Right? For example, in this case, event number 1 would be, so in this case, let's say event 1 is, what do you think?
The light is like, it's released.
Yeah, the laser the light shoots out, right? So, maybe a little better. That's a little better. Light leaves the floor. Okay? For number 2, it's light returns to the floor. That's just easier. Okay? So I start timing when the light leaves the floor, and stop timing when it gets back to the floor.
You have a
2
really
events.
fast hand.
What?
You have a really fast hand. You
I
have a
yes, that's fast finger. I do it that way. Right? So those are your 2 events that you time between, right? And events, remember, events that happen in one reference frame have to happen in all reference frames. So both reference frames are going to see those 2 events. Okay? But notice a difference. In Rosencrantz's reference frame, where does event number 1 happen? Here. Where does event, right, at the floor? Where does event 2 happen?
Same spot.
Same point, right? Good. In Guildenstern's reference frame, where's event 1? That's here. Where's event 2? Over here. Okay? So there's a difference in location here. That shouldn't be surprising. We learned about this, right? About how things change location. Okay, good. But it allows you to define something that is called proper time. Proper time is the time measured between two events that, I should say, in a reference frame in which the events are in the same place. Okay, so you have two events, you're always measuring between two events. You look at your reference frames and you look for the one where both events are in the same place. So when we look at this, which events are in the same place? Rosencrantz or Guildenstern, which one has the proper time? Rosencrantz, they're in the same place. Guildenstern, they are not in the same place. So this one, Rosencrantz is the proper time, Guildenstern is not the proper time.
What if he had tried it a little bit of an angle on?
Then neither reference frame would have the proper time. And you would need some more difficult machinery to work with. I will give you that machinery later. For now, don't worry about it. You'll be given problems where one of them has the proper time. Okay? Yeah, it's true. There's an infinite number of possible reference frames, right? Only one of them has the proper time. If you're not given one of those, you're out of luck. We will learn to deal with that, but right now, don't worry about it. This will be fun to deal with. Yes?
Why is proper time?
Why? What an interesting question. We will be able to answer that better later on, so I'm going to wait on that until we talk about space-time dynamics. But for now, I can just tell you a few things about it. First of all, that our equation is this. TP is proper time, okay? The time you measure in another reference frame is gamma times the proper time, okay? So when you're doing these calculations, sometimes you'll be given the proper time, sometimes you'll be given the other time. You have to figure out which one you're given. That's actually the only hard part, and then you just do a little math. Yeah.
You said there's like so many reference frames of like time.
You'll always be given one of them. For now, you'll always be given one of them with the proper time. Trust me, I'm Grasshopper. We will be learning more things, right? But for now, one of them will be the proper time, and you'll be okay. Yes.
With the homework, are the
Some of them. Gamma, I always give gammas that are 0.1, 0.3, 0.4, things like that. So you should always do your gammas by hand for practice. Okay? You should be able to do gammas like, come on, you can memorize them if you really want to. Right? There's only 9 of them to learn. Right? I mean, I could give you a few others, but you should be able to do your gammas really fast. Because they're going to be in every single problem. So those you can do. Some of the other numbers might not work out easily, and that's fine. Go ahead and resort to calculator against you then. For the time for this process, right? When we want to figure out the time in another reference frame, then you have to figure out, okay, so I'm given a time and I want to know what it is in another reference frame, right? I calculate the gamma factor from the velocity. So I just need to know, am I given this time or am I given this time? You can look, the answer will be different, right? The gamma, so it'll be either times gamma divided by gamma, basically, right? So we have to know, am I trying to solve for t or am I trying to solve for TP? And the problem will tell you that, like explicitly. So you have to think about the problem and say, like, which one of these reference frames is the proper time, right? And so am I trying to solve for the one that has the proper time, or am I trying to solve for the other one? In our problem, we were trying to solve for t, it turns out. Okay, because we were given it in this reference frame, which is the proper time. So we were given the proper time, we solved for t. But you might have been given the opposite, right? So that's why you have to think about it. This is the hardest part, the only hard part. The rest is very simple. It's very straightforward. Yeah.
Why'd you say, like, we only have to memorize 9 gammas? So
Oh, because I only give you 0.1, 0.2, 0.3.
Oh.
I mean, every now and then I might give something else, but not often. Yeah. B squared. Velocity of one reference frame relative to the other reference frame. The direction doesn't matter since it's B squared, so you don't need to worry about that one. Nice relief. We will have to come back to that, but they'll be symmetrical, right? One will always be moving to the other, so the other one's moving. Like if this was going 0.5c relative to this one, this will be going negative 0.5c relative to that. And since we're squaring it, the direction doesn't matter. So you don't need to worry about that right now. You will eventually, yeah.
So then, in the problem from the homework with Rosencrantz, the velocity would have been 0.36, that's how fast the
Yes.
Okay.
Right. Good question, Tom. Okay, so that's going to be the whole thing. And a little note about proper time that's useful. Proper time, you can just get it out of this equation. Gamma, this is always greater than 1. Notice that? Remember that? We came up to a number that was slightly more than 1, and then it got bigger. Gamma is always greater than 1, which means that t is always greater than tp, which means proper time is always what? Smallest, right? It's always the shortest. Okay? That's just a note that you can sometimes use as a cross-check if you want to make sure this is working out right. The reference frame of the proper time should be the shortest time. Okay. There's actually one more thing to teach, but it's really fast because it comes just directly out of this. Okay? This formula we call time dilation. The dilation means to get bigger. The time gets bigger. All right. Now, here's an interesting one for you. Let's say you're traveling from one star to another. Okay? Now, in the star's reference frame, everything is pretty straightforward. You get your ship going fast, right? And it takes a certain amount of time to reach here and everything's good, right? The ship takes a certain amount of time, and if you want to measure the distance, you can take the distance if you wanted. It's just the velocity of the ship times the total time it takes, right? Okay, now you're in the ship's reference frame. In the ship's reference frame, what are the stars doing? The stars are moving, you're staying still, right? It's not a big deal. Here's the star moving, the stars are going like this, right? Okay? Good. Here's the thing. In this reference frame, the time is different. Right? Which of these reference frames has the proper time? Let's think about this. This is important. Don't say it out loud. Think about it for a moment. Which of these reference frames? This one or this one? Which one has the proper time? Okay, the 50% chance of guessing. So let's just not guess. The question is, someone tell me what two events are we measuring between? Good. The ship leaves one star, and when it arrives at the other. Okay, so the question is, which reference frame does happen in the same place? Go ahead.
From the ship's reference frame.
Good. The ship's reference frame is the proper time. Make sense? Do you see that argument? Okay. And that means, so this is the proper time. This is the t, right? So proper time in terms of t is going to be t divided by gamma. If you just look at that equation, right? That's straightforward, right? Okay. So here's the thing. The ship is still, or the stars now are like moving, right? The stars are moving at the same velocity as the ship was, right? The time, though, has changed. Right? If the time has changed, what can you tell me about the distance that is measured between the stars? The distance has to now be Vt over gamma. Because the time is different, right? Time is t over gamma, so now instead of Vt, it's Vt over gamma. Okay, so from this, we can get another effect that falls right out of the fact that, look, we have velocity equals distance over time, right? Well, look, if the time starts changing, then guess what else is going to have to start changing?
Position.
The distance is going to have to start changing too, right? That's all it is, right? So if the time changes, anything related to the time also is going to change. And that's going to include the distance. Okay, so now we say the distance is also changing. That's saying the distance measured between the stars is different. Us looking at the stars will measure one thing. The spaceship looking at the stars will measure something different. Okay? This effect is called length contraction, and it's actually easier than time dilation.
That's never a good sign.
No, I'm thinking. I mean, you could argue that's not a good sign, but okay. why don't we, I think I want to talk about this in a little more detail. Why don't we push the quiz to Thursday instead? And so that I can spend another day to make sure we cover this. And I'm going to alter your homework slightly, so let's just focus on one thing at a time. I think that's a better idea. I think it's good. This starts important to get like nailed down. So let me spend one more day on this. But I will tell you briefly, because we have a little time. I mean, I don't want to leave you hanging here, but it's not much to it. You see it right here, right? The distance changes by a factor of what? Well, 1 over gamma, right? So here's the length contraction formula. Got to guess what LP stands for? Proper length. Good. Okay. Why don't we hold our thought on the proper length, on the length right now, and that way you can work on your homework and get used to this idea. And then on Monday we can talk about some more. I think that's all right.
Sweet.
All right, good. So you guys have a good weekend. We'll see you on